ma'am.
We are going to include what is categorical data, what is incidence and incidence rate, and what are the statistical tests involved, and how. As we all know, the categorical data is based on the qualitative characteristics such as race, gender, something else that doesn't have a number associated with it. If it like pain scale, as already Sarah mentioned, or bromate scale, if it doesn't follow an order, it is called nominal. Sometimes it can be dichotomous, like alive or dead, cured or not cured, abnormal or normal, tall or short. It can be recorded as a even or counts and can be measured as a proportions. Why? The timed events like vomiting every hour after the surgery or death in cancer patients can be measured as a rate. Often the measuring as a frequency, it tells how much risk is there between the outcome and exposure, while measuring as a rate tells how many number of cases in a population occurring over time. Before going to analyze the data, we have to tabulate the collected data into a table using contingency table, depending upon the number of items. If there are 2 groups, we have to use 2-way table. If there are 3 groups, we have to use 3-by-3 table. To analyze the categorical variables, normally we use chi-square test and its variance. If it's a paired data individual, we can use either McDermott's test or Cochrane's Q test. If it's an unpaired data, that is data collected from different individuals, we can either use chi-square test or Fisher exact test. The Fisher exact test, the chi-square test is a non-parametric test that follows chi-square distribution. It is a continuous probability distribution. It is skewed to the right. As the value is squared, it is skewed to the right. The shape of the chi-square it depends upon the degree of freedom. Normally the degree of freedom is the extent of freedom enjoyed by a given set of observed frequencies. Normally it is n-1, that is the number of categories minus 1. If it is a contingency table, the calculation of the degree of freedom will be the product of row minus 1 and column minus 1. As the degree of freedom increases, it will become more and more symmetrical. If it goes beyond 30, it is the number of categories goes beyond 30, it will become normal distribution. To do chi-square statistic, there are some conditions. The data must be in the form of frequencies, and the sample observation should be independent, and total frequency should be more than 50. And the expected cell frequency should not be less than 5. It is used to test the hypothesis of goodness of fit, where the hypothesis will be the distribution of analyzed variable is same as the hypothetical, and used to test the hypothesis of independence. It is the hypothesis of variables that are analyzed as independent, and to test the homogeneity. Analyzed variables are distributed equally between the groups. Let's see an example. A warden expected that the preferences of an ice cream flavor among the inmates of hostel were equal in distribution. To do this, a sample of 100 students were asked regarding their preferences. With this data, can we say that the preferences are equally distributed among the students? First, we have to make the null hypothesis. First step will be the null hypothesis, that is the preferences were equal in frequency among the students. The alternate hypothesis will be the preferences are not equal in frequency among the students. Second step will be the calculation of expected frequency. Here we have to calculate expected frequency by adding up all the observed frequencies. Here it is 100, observed frequency is 100, and the categories will be the flavors of ice cream. So divided by 5 is equal to 20. After calculating the expected frequency, we have to use the formula and we have to calculate the chi-square value. Here it is 6.3. The third step will be the calculation of the degrees of freedom. As the categories of flavors of ice cream are 5, as I have said earlier, it is n minus 1, so the degrees of freedom will be 4. With a 5% level of significance, the critical value, what we have to see is 9.48, which is greater than the calculated value of 6.36. Let's have a look at the chi-square distribution chart. The area right to the critical value, that is 9.49, rejects the null hypothesis, while the area left to the critical value, it accepts the null hypothesis. As 6.36 falls in the left side of the chart, we have to accept the null hypothesis. So, to conclude, the observed preferences, the observed frequencies are equally distributed among the students as per the warden's expectations, which proves the hypothesis of goodness of fit. Even though chi-square has a wide range of application, it has some limitations. That is, data should be from random sample and the observation should be independent. It tells only the presence or absence of association, but not the strength. It won't give reliable result if the expected value in any cell is less than 5. In that case, Yates correction is necessary. I am not going to much into the detail of the Yates correction. If the contingency table is more than 2 by 2, the Yates correction cannot be applied. When the sample size is small, less than 50, and the expected frequency of any cell is less than 5, we have to choose Fisher exact test. It is an exact test using the hypothesis of independence. It gives the exact value even for smaller samples. However, the calculation will be little tedious and it's seldom attempted by hand. Now computer softwares are computing the Fisher exact test even for bigger contingency tables. It's more or like the chi-square test, so I'm not going further into this Fisher exact test. How to? You have checked the association between the two groups. Now you want to check or otherwise quantify the association between the two groups. That is what you have to do. Either you have to do odds ratio or risk ratio. To quantify the risk between the outcome and exposure and outcome, you have to do odds ratio or risk ratio. In any cohort prospective study, consider an example of smoking. You consider its exposure as a smoking and the disease will be the CLM. If you want to calculate the relative risk, it is calculated as a risk in exposure group by the risk in non-exposure group. The numerator in risk in exposure group will be the number of new cases, that is number of CLM patients. The denominator will be the population at risk during the study period, that is the number of smokers at the particular period of time. So we have to follow the individuals, total individuals at the risk till the end of the study period to get a valid result of relative risk. The relative risk always ranges between 0 to infinity. If the relative risk is equal to 1, the risk is same between the exposure group and the control group. If the relative risk is more than 1, the exposure increases the risk. That smoking will increase the risk. If the relative risk is less than 1, the exposure reduces the risk. However, in case control study, we cannot calculate the relative risk directly so we have to do odds. This case control study is a retrospective study. The odds of exposure among cases will be A by C here, while odds of exposure among control, that is non-exposed, will be B by D. So the odds ratio will be A times D divided by B times C. We can calculate the odds ratio from risk, relative risk, or relative risk from odds ratio, but it's not give exact value. For uncommon events like with less than 10% of incidence, both relative risk and odds ratio would be nearly identical. The result will be nearly identical. For common events, for common infection or common disease, the odds ratio will be remarkably high compared to the relative risk. So, whenever you are having that type of study, you have to be little caution in telling about the results. The odds ratio and relative risk should be presented with a 95% confidence interval along with the p-value. To get meaningful result, it should be expressed with log transformation, and you should not include 0 and 1 in the confidence interval. At the 0 of log of 0 is minus infinity and log of 1 is 0. So you should not include the confidence interval with 0 and 1. It won't be significant. It is always preferable to use the rate ratio instead of relative risk in longitudinal studies, which requires a long period of follow-up, because there is always a chances of incomplete follow-up. So to calculate rate ratio, we have to use incident rate in exposed group divided by incident rate in non-exposed group. Here, the numerator in the incident rate will be the number of new cases, while the denominator will be the sum of person time at risk. For example, consider a population size of 1,000. You are going to study for 1 year. The denominator will be 1,000 person years. If you are going to study the same population for 3 years, it will be 3,000 person years. The related risk ratio is always accurate, as it includes the person who is entering the study and who is leaving the study. So it's better to always do the rate ratio instead of relative risk. In this type of clinical study, compared to the calculation of number of patients, number of cases occurring over time, it is better to do how long they have survived over the study period. How long they have survived will be more meaningful. So here comes the survival analysis. It is a time to an event analysis. Time to an event is the outcome of interest. Initially, it is used for time frame analysis of cancer patients. Now it has been used for many other fields, engineering, agriculture, economics, everything, every field they are using the survival analysis. It is described in terms of two probabilities. Survival, it is from the specified time point to a time of event. It is a product of probabilities, where hazard is the instantaneous event rate at a subject which survived to time. The KAPLAN-MEIER estimate is the non-parametric estimate of the survival function. It shows that the probability of survival in a given length of time. It is commonly used to compare two groups. Consider an example. Here we are having 5 subjects. The study period starts from time 0 to the end of the study will be 12 months. How to plot the curve? Just on y-axis the survival probability is plotted. It is 100% for all the subjects. In the beginning of the study, the survival probability will be 100% for all the subjects. And time in months is plotted in the x-axis in equal intervals. The survival probability is 1 minus number of events of interest at time t and divided by number of subjects at risk prior to time t. At 4 months, subject E dies at 4 months. So his survival probability will be 4 by 5. Here the hazard ratio will be 1 by 5. That is 4 by 5. So the hazard ratio will be 1 by 5. Next, subject A, he drops out at 6 months. It is called censorship actually. It is a very important phenomenon in the experimental study. It can be either right censor or left censor or interval censor. Right censorship is very common. It means that a particular subject is known to have survived at a particular point of time. Here it is up to 6 months. Till that time, death or failure did not happen to that particular individual. After that time, it is unknown. We don't know. But he will be included in the study. As though he had left the study, he will be included in the study. That's a censorship. It can be marked in the step as a corresponding point of observation. It can be marked in the step. At 7 months, subject C dies. So here the survival probability will be 2/3 and the hazard ratio will be 1/3. See, overall survival probability will be 53%. Here the B and D objects, both subjects have completed the study period, but we don't know what happened after that. So we have to include them also in the study period, and the total survival probability for all the patients will be 53%. The survival probability is a estimate which is useful in calculating the survival over time. It can be used for other fields also, engineering, agriculture and medical field. It's very commonly used. It's developed only for medical field. Now they have been used in engineering and agriculture also. In economics also they are using. Finally, the take-home message will be the chi-square and Fisher test is used to test the association between the exposure and outcome, and odds ratio and rate to quantify the number of outcomes over time. While Kaplan-Meier curve, that is Kaplan-Meier estimate, taken the occurrence of an event.